So let me start, since there is a broader topic, a breadth of research interest in the audience. So I will start with a little bit overview to bring the topic into context. So first of all, compact objects, where they're coming from, they're born in the core of stars, of massive stars, about 7 or 8 solar masses or so. The star, so the core becomes iron, as all you'll know. And as the very moment as the outer layers go off as a supernova, the core collapses. So what remains after, it's either a neutron star or a black hole, and it's a neutron star if the core is smaller than a certain value, which I'll talk about in a moment. Otherwise, for value larger than a certain maximum value, where no force can sustain the collapse, the compact object becomes a black hole. Now, what is this maximum mass? This is a very important topic, and as of now, we know that it's larger than 2.14. As a matter of fact, I just updated this on the slide. I believe the first author of this paper is here visiting this week, so it was 1.97 up to, for a number of years. So we know it's larger than this. It's smaller than 3 is very much of an upper bound. But where it is, the precise value is a very important question, because it's very much tied to the equation of state of a neutron star. So it's something that we don't know, but we would really like to know. And it will come back throughout the talk. So compact objects are born in interior stars, but something which is of interest to us, and especially today in this talk, is the fact that they are often found in binaries. Now, how do they form in binaries? 2 main scenarios, very generally speaking. One is as isolated field stars. 2 stars, they are born as evolve as a binary, and when they go off a supernova, the compact objects still remain bound, and a fraction of them remains so. Otherwise, compact objects that are isolated can actually become bound through dynamical interactions, and this happens especially in dense environments like globular clusters. So this is just, I mentioned just as a broad overview. I've also been working lately in this, but I won't be talking anymore today. However, just to mention, just this area of binary formation is taking off in the last few years as an area of research on its own. So it's a lot of interest just in learning how binaries were formed. As far as we are concerned today, what we care is what happens when the binary loses a gravitational wave, and if that happens on a time scale which is shorter than Hubble time, then they will become particularly interesting to us, as binary compact objects are the strongest sources in LIGO and Virgo. Okay, so with that introduction, so what I'll be particularly focusing on is the connection between gravitational waves and electromagnetic counterparts, and what we can learn when we combine the two. So this slide, it's a busy plot, and I will go through one by one, but it will be very relevant for the future as I discuss more quantitatively some results. So first of all, we have 2 compact objects with 3 types of possibilities, so binary black holes. So for binary black hole merger, the end result is another black hole, more massive, mass, sum of the 2 minus the 1 that's been lost to the energy that's been lost to gravitational waves, but it's the simplest possible situation. Next, in the level of complication is that of a neutron star black hole, and here already we can have, broadly speaking, 2 possibilities. They are very much dependent on the mass ratio between the neutron star and black hole. Where precisely this mass ratio is somewhere between 3 and 5, but it's dependent on the equation of state, which is something important. So why this difference is because what matters when a neutron star and black hole merge is whether the tidal disruption radius is inside or outside the radius of the last stable orbit. So if the radius of the last stable orbit is outside the tidal radius, then the neutron star gets disrupted outside this radius, and it can form an accretion disk. An accretion disk, as we'll see later, is an important element when we're discussing electromagnetic counterparts. And this is for mass ratios below 3 to 5, again, with precise value depending on equation state. Then we have the binary neutron star case, which is the one more complex and with more possibilities. So first of all, let's look at the outer branches here. So this is a branch where the sum of the two neutron stars is larger than 3. Let's call 3 as this, since we don't know where it is the maximum mass. So let's say 3 is the absolute value, so it's larger than 3. Then the compact object left behind is a black hole. So that's one first thing. On the other hand, let's go at the other extreme, where the sum of the two is smaller than this maximum value. It's again 3, let's say, whatever it is. Then the two neutron stars can actually end up leaving behind a neutron star compact object behind. And then in terms of what can happen to the material and therefore to potential electromagnetic counterparts, it's also dependent more on the characteristics of the merger and the initial neutron stars which merge. So here it matters also the mass ratio. If the two neutron stars have identical mass, numerical simulation have shown that there is no mass in the disk left behind. Basically, the mass produced in the disk goes to 0 as the masses of the two neutron stars become equal. So for equal neutron star, which is an unusual case because you have to be, they evolve independently, so you had to, have to be very unusual again to have them have identical mass. But one thing to remember is that there is this dependence on it. So the more unequal they are, the more mass will be created in the accretion disk. So that's the situation with again no accretion disk. On the other hand, if they are unequal, which is this situation here, there will be an accretion disk. Again, the mass will depend on it, how much there is. Then there is just here yet another possibility as the two neutron stars evolve. And this is a situation which is referred to as a hypermassive neutron star, which is a neutron star that, if it were not rotating, would end up forming a black hole. However, it undergoes an early period of rapid rotation. Hypermassive is referred to differential. Supermassive is generally referred to solid rotation. This is just jargon. But basically, the bottom line is that if it's rotating, there is a period during which the centrifugal force basically help preventing collapse for a period of time. Then eventually will slow down and collapse onto a black hole. So whether this forms a disk or not is still somewhat debated. According to the picture by these authors, short-lived would not form, long-lived may form, maybe due to some mass shredding. In reality, this situation is still not quite understood because there could be also winds from hypermassive neutron stars that could help drive electromagnetic radiation. But just this whole picture illustrates the richness of the situation when it comes to electromagnetic counterparts to gravitational wave events. So with that in mind, so with the picture in mind, this is just a very brief summary now. So binary black hole merger, no expectation for an electromagnetic counterpart. I put this just for historical note, for those of you who haven't followed this as closely. During the first binary black hole event was accompanied by I don't know how to call it, it's not detection, like Fermi they call it detection, but a possible counterpart which was within alpha second by the Fermi collaboration. It was highly debated. The sensitivity, different analysis led to different results, but it was very exciting in its own as a possibility that led to a lot of ideas regarding what could cause it. But I won't be saying anything about this. So this is just remains as a historical note until maybe, hopefully, one day there will be some real detection. Okay, so going on the other end, so continue on neutron star, black hole, neutron star merger. So I'll be talking more about this. So the summary from the previous slide is basically there is an accretion disk for, in this case, for depending on the mass ratio, for neutron star merger. In most cases, we expect it. Now, one extra step. How do we go from, so again, so we have this accretion disk, and so Yeah, this is basically the picture just in my PowerPoint that drawing. But the idea is that the accretion disk will drive some radiation, and I will go through all the steps of it more quantitatively in a moment to describe. But this is just an overview picture. And for a long time, this merger of two compact objects was believed to be observed as short GRBs. Now, for those of you who are not working on GRBs all the time, why short? Because I'll be talking about short, but you may wonder, okay, why short and not long? Reason being that this burst of gamma radiation, which had been discovered and studied from the 90s, they showed that from the very beginning a double peak in duration, and with a lot of imagination, some astronomers call the longer ones with long GRBs and the shorter one with short. Now we know that the long GRBs are associated with the collapse of massive star. Andrew was Andrew's main Andrew's here, or no, his PhD thesis was on this model, and whereas short GRBs were believed to be associated with you know, a compact object merger, but there was really no proof, so to speak, until more recently, which is something I will get to later in the talk. Okay, so now this was with in pictures, and now let's go through some of the work that has been done in understanding this picture and establish it theoretical and numerical. So what this shows is a numerical simulation of an equal binary neutron star. This is done by the with the WISCI MHD. There are 3 codes in the world that do this type of simulation, and WISCI MHD is one of them. So these are 2 unequal neutron stars. So this is the accretion disk. It's not really much of a disk, but it's more of a torus. It's a hot torus, and study of this is in its own rich area of study, because they're very different than the disks in AGNs. So they're very thick, as you see here. But this is basically the matter that eventually powers the radiation that we see. So this is the starting point. So we have a black hole now. The simulation was set up with 2 neutron stars, which are unequal, and where the sum of the 2 masses was larger than the maximum value for the equation state considered here. So this is step 1. Step 2 of this big picture that we're building is how to launch a jet. So gamma burst, we have evidence from observations that the emission is not isotropic, but is jetted. So something in which simulations are working now, and there's a lot of effort goes in this direction, is trying to produce jets as opposed to just put them in the simulation and then let it propagate. So this is still in infancy as far as the actual production of the jet, again, because often when you see a jet propagating in simulation, the jet is imported as a source of energy, as a piston, as they call it, and then let it evolve. As it is right now, so there is some evidence, and this was the first paper that reported on some of that. The way what we call a jet is more of a poloidal magnetic fields. So the idea is that you have magnetic fields, again, generating during the merger, that if a poloidal configuration is conducing to accelerated particles in that direction, and therefore launching jet. So just to keep in mind, building all the pieces of the picture as we go from a merger onto all the way to the radiation that we see. So we're going through every step. And that was 2011, so it was the first paper that actually did that. In the last few years, there have been several groups, and one with also a former postdoc, Bruno Giacomazzo, and then his own postdocs. So this is, so more groups, basically bottom line, are finding similar results. Here what we did was running several set of, these are all GR-MHD simulations with different inclinations, different equation states. And basically, bottom line is that in all the configurations, some more, some less than others, there is evidence for some basically magnetic field with some jet-like configuration, if you wish. So this is basically a simulation I started to show that during these mergers, well, we have the source of energy that we knew from matter, but we're also able to drive jets. And it's again, this is a very active area of research, but simulations are starting to point in that direction. And now the last step of, so we conclude this whole picture of how we go from a merger all the way to the radiation that we see. So we have a jet, we have a merger, we have a jet. Now what comes next could be a black box, and in fact here's where the analogy between short GRBs and long GRBs exists, and the fact that the two have a lot of analogies is because what happens next is mostly rely on the fact that you have a sudden injection of energy with some characteristics, which can be very generic. So the source could be an exploded stars, like for long GRBs, or could be a merger. But the point is that the idea is that there is a lot of energy released within a small volume. So some of the ideas it's contained in this so-called fireball model or internal-external shock model. And the idea basically, this during this process of launching a jet, there will be a lot of uneven shells being launched, and during collisions, some of the energy is released and basically released in high energy particles. So this is very much in a nutshell, and this is the radiation that we see. We call prompt. We see it in gamma rays. As time proceeds, then all these shells collide with one another and will start slowing down in the external medium. So it becomes like a giant supernova, except that this is highly relativistic, but eventually will slow down. And that produces the longer wavelength radiation that we see and that we call afterglow. So this is a very broad picture of the main electromagnetic counterparts to binary mergers. And I should say here there's another very important component, which is the kilonova, which I will not be discussing. So that's an all separate story. So it's not. So this is not all the electromagnetic counterparts. So the other main one is the kilonova, but this is the main one associated with basically the accretion disk and the launch of the jet. So we have fully closed the picture now, understanding in 10 minutes, 15 minutes, how we go from the very first step of a binary merger all the way to the radiation that we see. So now we can discuss, so now that we know how to produce the radiation, so we can go to discuss more what we can learn by measuring both of them. And this is a very highly incomplete list of the many things that can be done, some of which have already been done by combining two observations. So these are just some mentioned constrained compact object formation channel relocalizations. For example, if we just have gravitational waves, as you know, gravitational waves are very highly delocalized. So in order to be able to localize where the mergers occur, we need to have the electromagnetic counterpart, because with electromagnetic counterpart at longer wavelengths, we're able to actually resolve the galaxies and see where they are, and therefore learn about the compact object formation in independent ways than what we can learn with gravitational waves alone. Independent measure the luminosity distance and redshift, measure the Hubble constant. Will far here is also written. Well, this has already been done with just one event, but when you have many events, this can be done better. Of course, constraint difference between speed of light and speed of gravity, new test of equivalence principle, learn about origin of heavy elements, so many things, among the other, probing jet formation, speed evolution, physics of the merger, association with short GRBs, which I'm leaving as a question mark for the time being, and also learning more about the equational state of dense matter. So these two topics, there is many, again, the list is still incomplete, but for the rest of the talk, I will be focusing more on these two aspects, which have been the ones I've been mostly working on myself. So just one side, again, for those of you who don't think about equational state all the time. So the equational state is, as the term says, is the relation between pressure and density in very, very dense matter. The fact that we do not know reflects our ignorance about nuclear forces, essentially, on the nuclear scale. So over the years, there have been lots of people investing lots of energy and time doing calculations with different methods, making different assumptions for the types of particles that can be in the nucleus. And there are a lot of models. So this is just an example recollection from Jill Latimer, actually Steinberg, one of the experts in the world, major experts in the world on equation state. How do we go about measuring? So traditionally, what has been done is basically well, it's shown in this plot. So the main point is that for every equation state makes a specific prediction for a relation between mass and radius of the star. So that's it's a one-to-one correlation. So what then astronomers have been doing for many years is measuring mass and radius, or trying to measure mass and radius independently, and then with that trying to get some constraints on the equation state. Now masses are measured from objects in binary systems. In fact, the last, the neutron star 2.17 that's how it was measured. So they're relatively more precise. So they have some errors, but they're, in some cases they can be reasonably well constrained. Radii have always been a very sticky points with lots of measurements, or way to measure it being made. Typically, the most common ones have been via pulse profiles in through the of the X-ray emission, also X-ray burst. But each of these methods has its own issues, and also there is anytime you measure radius, there is always a degeneracy with distance. So there's always been very much of a problem, because as you merge, there is no way to measure a radius without directly unless you know very well the distances. So these methods, people have done and tried to do their best. There have been some constraints, but basically they're limited by by the reasons explained. So where are we now? Well, gravitational waves have opened an all new windows on the ways to study the equation state of neutron stars. So this is an example now for one particular equation state. So what are we seeing here? So these are solutions to the TOV equation. For again, it was one particular case that we studied with my former postdoc, and for which I will show a simulation. The point is that, as already mentioned before, given two neutron stars, once they merge, whether they exist as a stable neutron star or as a supermassive, hypermassive neutron star, or collapse to a black hole, is something that's equation state dependent. So here, these are lines, stability lines, which depend. This is one particular equation state, but every one will have its own difference. So that's one thing to keep in mind for the following. Now, what this blue line shows here are so we consider here for this study to see what happens to two neutron stars, where we had for the equation state that we consider the sum of the two neutron stars was below the maximum mass by this equation state. And what I showed, this is the simulation. If I can point the finger in the right place for starting. So this is was the first GR emission simulation to say with where instead of considering neutron star that collapse into black hole, which was typically studied in the literature, we studied the case what happens when it forms a neutron star, and also we were able to then study the characteristic of the objects that was left behind. And we found growth in magnetic field, which was very interesting because this was basically, it turned out to be another way to make a magnetar, but also it's particularly interested in light of a fraction of these merger events that can produce a neutron star, because if you have high magnetic fields, they are a source of energy at early times. So it's interesting in terms of, in light of drawing energy. Later. So this was almost a month of running time on a computer, I have to say, on a supercomputer, which, and this is the merger product. It was not completely, so at the point it stabilized, also although it was not spherical yet, but we ran out of time on the computer that we had at that point. So going back to the equation state, so this is for this particular simulations, this is the gravitational wave signal that's associated with it. So this is one particular case. Now, why gravitational waves are so interesting in respect to the equation state is because they are very sensitive to the equation state of neutron stars. And this is just an example from later work where we study, so always via GRMHD simulation, a sample of different, well, we started here with identical neutron stars which were the same in all situations, so the same mass, but only varying the equation state. So it was basically a study of the equation state and its dependence on, so basically the merger product and the gravitational wave signal, how that depends on it. So this is just a visual without having to describe one by one, but you can see just again visually how much they differ. So they were identical neutron stars, again same configurations, starting point, only different is the equation state. So bottom line is that gravitational waves are extremely sensitive to power to probe the equation state. However, the point is where are we now in terms of what we can do with the current instruments, at least for the next few years. The problem is that as we are right now, in order to be able to actually use gravitational waves in a very powerful way to infer the equation state, we have to be able to measure the signal post-merger. Post-merger, the merger line here is when the differences become mostly pronounced, and then the sensitivity to the equation states becomes extreme. However, even in the very good case of GW 1707, we measure up to, there was 8, Katerina, something before, so the signal went out of the LIGO sensitivity band. Well, it was up to 8 or so. It was up to a few cycles before.
100 hertz.
So, okay, right, in terms of hertz. So it was an area where there are, I mean, as you see here, there are some different. There is some sensitivity because this is the area where basically you start to probe the compressibility, the formability of your star, which is a measure of the equation state. So there is some information, but it's not as strong as it could be. So while waiting for either higher sensitivities or a lucky neutron stars merger in our backyard, the question arises whether we can still learn something when more on this topic on the equation state by combining gravitational waves with information from the electromagnetic counterpart, which is sort of the topic of today. So in that respect, going back to something I already alluded to multiple times, is this dependence of the equation state on the, the dependence of the merger product on the equation state. So what we did here was taking the distribution of masses of neutron stars. These are observed, so nothing special here. And then in different equation state, we calculated what the product would be. These are just 4 or 5 representative equation state, and the lines here mark different regions. So this is neutron star, SNS is the intermediate one is supermassive neutron star, and then it's black hole. So basically, again, without focusing on the specifics, what should catch the eye already easily is the fact that there is a very strong dependence in different equation state on the merger product. So, for example, this equation state that would predict a very small number of either supermassive neutron star or black holes, none, and then other extreme where you would predict more to be black holes. So the question is now, how can we learn more about what the remnant is if we don't see it from the gravitational wave signal? And this is again a place where electromagnetic counterparts can help. So going back to some observations that were made years ago. This is before the gravitational waves discovery. And they were early time X-ray observations following short GRBs. So these are two examples of something that hopefully can be done more in the future. So what these two figures shows are, so again, this X-ray data. So what here you see, following the short GRB, then there is a period where the luminosity was much lower, but you see basically there was a plateau in the luminosity, and then followed by decay, power t to the minus 1/2, which is very suggestive of a neutron star, of a highly rotating neutron star. Basically, this luminosity tracks the luminosity of spin down by dipole.
It's not either on that data points. I mean, you drew this very complicated.
Oh, this is not mine. Yeah, I'm not. So this in this one here. Somebody drew. Yeah. So there are. Yeah, I don't. This is a very short time. So in near. So I don't. So I think the data that they have is the data that they're plotting here. So it is. So this data. I mean, you could also argue that draw in different ways. So that's. So which is why I'm showing them just as a representative, but not as a, concluding anything. So it's an example of what one could do with early observation. So yes, so this is, I agree with you that one could think of different fitting. But the idea, so basically here, this is the slope. It's also the spectra was different. So here it's the early gamma ray, and this is the slope. So it's the most natural, but yes, you could argue, I don't know if they tried to fit something, looks maybe a bit less like with a single line. But here the radiation was more in the X-rays, so this was more gamma rays. So it was also, there was a spectral changes. And this is a situation more another extreme, so to speak, where there was the prompt emission, and then there was a very sudden drop. So again, as they interpret it, as the fact that here this may be suggestive of the presence of a neutron star, whereas on the other end here, there could have been a supermassive neutron star which suddenly turned into a black hole to explain this very sudden drop in energy. So the point is that understanding these early phases now is very important, and in fact this is something where with my collaborators we're working on, because it's so using electromagnetic counterparts, so observation at early times can help constraining the compact object remnant, and then you have from gravitational waves you have the masses. So if you have the masses from gravitational waves and electromagnetic counterparts give you information on the remnant, then you can say something on the equational state. So the two together are more informative, at least at this stage, for a number of years than gravitational waves alone. Okay, so now last sort of third of the talk, we'll be discussing a bit of speaking of neutron star counterparts, electromagnetic counterparts. Obviously, there could be no talk without speaking about GW 1707. Which is now, I mean, it's 2 years old, but there are no younger siblings, so we keep on giving a lot of attention to the first one until hopefully a new one will come. So yeah, I'm sure you've heard a lot of like the general framework here. So there are 2 neutron stars, and they were seen in pretty much every wavelength in which they were observed. So it was the beginning of multi-messenger, I should say, photon astronomy, to be fair to neutrino astronomy. So we always say it's the beginning, but there were neutrinos before that. Yeah, and I won't go into describing any much of this in detail, since I'm sure you have all heard about the general observations. And so seen at every wavelength, and just to put in context. So this is the gamma rays. So as I was explaining before, so it's the one that we believe generates in this jet, and then the afterglow which I described before, this longer wavelength radiation, just to put in context of the theoretical framework in which we interpreted. So, question is what we have learned so far from this event, and the list is extremely long here as well, as you probably, unless you were sleeping those days, there have been a larger number of papers just in the first few days alone. And again, a long list of topics that affected all areas of astrophysics, from nuclear physics to cosmology. So yeah, there could be endless talks given on this subject alone. However, for the remaining of my talk, I will be discussing a little bit more what we learn about the jets, and also now making a bit more the connection with the short GRBs, to which I kept on alluding throughout the talk, but never quite making that connection. All right. So there was a first question that arose when this event was seen. And there was this GRB 1707-0817, a standard GRB. So why was this question posed to start with? The answer maybe is in this plot. So what this shows is a collection of long GRBs, short GRBs, and then GRB 1707-17A. So the one thing that seemed to struck, or at least was noticeable, was that this event was much dimmer compared to the short GRBs that we were used to study and loved and were familiar with. So it was not obvious from the very beginning. We kept on observing short GRBs, cosmological, and then we saw a double neutron star merger event with some radiation that resembled that of the short GRB, but was much dimmer. So the question came, is this really a member of the same population, or maybe we are seeing something else, which could have been very much possible. So there have been many papers on this topic. So I will describe more the ones by our group, but I should say there's been lots of work. Also, Andrew and students have done quite a bit on this. So the point to start with, the point of this lower energy, lower luminosity is not surprising to start with. So for the standard cosmological short GRBs, the typical emission angle that has been measured from the afterglow radiation is about 16 degrees. This is measured from afterglow observation. So assuming that this is now a regular short GRB, then what is your likelihood to see it on axis? That's about 120. So the point is that when we're looking at this short GRB, so this is just angular size of the sky, like roughly. So if you have roughly 6 degrees, it's your angle on the sky is about 120 of the whole sphere. So the main point is here, as we're looking at short GRBs and we detect the cosmological ones, we're detecting them on axis because we're preferentially detecting brighter events. On the other hand, this event was detected via gravitational waves, which don't care where the axis is pointing. I mean, there is some preferential direction in LIGO, but it's definitely not as strong as in gamma rays. So the fact that we may not see on axis, is not a surprise. So what we did in our group, this is as the data were not quite public yet; they were more in the rumors. So basically, what we took was a simulation which we already had of a standard short GRB, and say, okay, let's see what we have, what radiation we would be seeing if we happen not to see it on axis. So we basically studied the radiation as a function of the viewing angle, and there are two main pieces that one wants to look at. One was the radiation, and I'll describe it in a moment, this curve, and the other was the time delay. So if you remember from this event, there was a time delay of about 1.74 seconds between the gravitational waves and the gamma ray signal. So that's the other element that you want to be able to explain. So long story short, so So here we have various curves because again the data were not published, so we didn't know whether it was thermal, non-thermal spectra. So we did a number of different experiments. Then it turned out to be non-thermal. So the curve that would matter would be the purple one here. So luminosity on the order of few times 10 to 46 would be achieved for a viewing angle somewhere between 20 and 30. Now let's look at the observed duration here. Let's look about 2030, and here we are with a time delay of around 2 seconds or so. So basically, bottom line is that this event, this is from the gamma ray component, we'll get to the afterglow in a moment, look like very much like a normal GRB, like a relativistic jet seen at some angle. And again, both the luminosity and the time delay are naturally reproduced like that. So now, weeks and months went by, and this whole afterglow radiation was observed. So then you wonder, okay, now you take your same model, and let's see whether you have to be able to reproduce also the afterglow light curves in all bands. So this is what we did, but before showing the fits, let me just describe a little bit of the afterglow, the shape, why they look as they look. So what you have here, you're observing some angle, and there is a relativistic outflow. Now, in the relativistic outflow, your radiation comes due to Doppler beaming within 1/gamma. And the radiation is mostly, so the jet is mostly intense along the axis, and then the brightness basically declines with this on the side. So just let's try to understand, first of all, physically, just qualitatively, what this translates into the light curves. So basically, at the beginning, one starts by seeing a certain emission within a certain angle. Now, as this propagates, it slows down. So what the observer sees is a larger and larger angle. And at some point, the old jet, which is very bright, is coming into the line of sight. And that's when the curves are reaching a maximum. After a while, as it keeps on slowing down and the 1/gamma are largest, one starts seeing, again, also radiation from the other side, which is less bright. And then one has the decline in the light curve. So this is just a qualitative explanation of the behavior of the light curves. Quantitatively, the specifics will depend on viewing angles and interstellar medium and things like that. However, so basically, but with the same energetics and so the same jet parameters that were used for the gamma radiation, we were able to fit the afterglow light curves. And this is when the paper was published. These are the data. Then this is like much later when basically it kept on being observed. So the curves were basically also predicting where they would go. So summarize. This is a very important now point. Is basically GRB 1707 17A is for it basically behaves like a normal standard short GRB. And I should say that this was not, so I am bringing this up now, but this interpretation was indeed not the very first one made, as a matter of fact, because there could be also, there were other ideas being proposed, for example, like a relativistic, a non-relativistic outflow, or mildly relativistic, more spherical, where the shape of the light curve was basically fitted by having a profile, a velocity profile in the ejecta. So in the case of a jet, it comes natural because it's a viewing effect. So you're reaching the maximum as you're reaching where the jet is emitting the most. If you don't have your geometry and everything is spherical, then you have to have an extra degree of freedom in order to fit the slope, and that extra degree of freedom was being used here by having assuming a certain velocity dependence in the ejecta. So, as I said, so the fact that this event that was a standard GRB was not clear from the beginning. So it was debated in the literature for a while. Eventually, it was a VLBI measurement, 207 days later, after the event, completely settled the issue, and they showed very clearly via VLBI observations that it is indeed associated with the relativistic jet. They measure superluminal motion, which is a key signature of a relativistical jet. So basically, by now, we know this event has been very, very important for many reasons, but including one that I described here in settling this issue of the origin of short GRBs. So we have known about short GRBs for several decades, since the late 90s, but now we know that they're associated with double neutron star mergers, maybe also to neutron star binary black holes. So this is something which is still open debate. We'll have to see for one event when it comes, and we'll undergo same type of study. So last few minutes, Matteo? Yeah. Okay, so perfect. So basically, so just last few things. So just looking in the future now, more and more what we can learn. So continue more in this work. So we're continuing more in this work basically on trying to extract astrophysical information from electromagnetic counterparts to gravitational wave detecting events. So what we're doing, this is a joint collaboration between with Davide Lazzati, which is more expert on the light curves calculations, and the GRMHT group with the jets. So we're basically coupling a jet, so producing a jet within, so we're coupling the GRMHT simulation that I showed early on from a binary neutron star merger with jet propagation. We're basically propagating a jet in the actual environment produced by the GRMHT simulation. So this is work ongoing. This simulation has been running for a few months now, but that's the direction in which, so one side we're going numerically. On the other, given, here you do one simulation with one specific case, and it takes a lot of computer time and months. So at the same time, with Davide Lazzati, we've been then asking ourselves, can we try to learn from the numerical experiments that we're doing, plus with just purely astrophysical considerations on jets? Can we learn something, with analytical modeling? So basically, what we've been doing is trying to extract some physical key physical elements that regulate the jet propagation in environments of different types, so different masses. So this is like light curves. Light curves. I'll get to them eventually. Let me get to the light curves because those are more interesting or more directly related to observable. So those were jet properties. Basically, what we're seeing here are how these afterglow light curves vary in environments with different type of ejecta masses. These are delay times between the merger and the engine, different velocity of the ejecta, and so on. Now, why this is irrelevant, I may not have, I said it, but maybe not as directly. So remember, I was discussing how the ejecta mass depends on the different masses between neutron stars, but also depends on the equational state. So this is again a place where, if from gravitational waves we're measuring the masses, which is the main thing we're measuring. For the ejecta, we need to rely on the electromagnetic signature. Kilonova, it's yet another way by which they measure some fraction of the mass in the ejecta. But also what we're doing, so on the side, as an additional, is exploring the dependence of the light curves themselves to the ejecta in which they expand. So basically, putting all this together, learning more about the physics of the jets themselves, and also more about the equational state of neutron stars from more events. And with that, summarizing, so detection of gravitational waves in connection with the electromagnetic emission from binary objects have had and or are going to even more, having a very profound impact on a lot of problems from energy astrophysics, gravity, nuclear physics, and cosmology. And that's it.
Question to Rosalba.
So you showed some light curve. So you showed how the light curve depends on the nature of the remnant object. In that paper, if I'm not mistaken, the paper was for a classical top hat short gamma ray burst, while the 170817 is likely to be structured.
Right.
So have you computed the light curve like for the structure?
Right. So basically the point is that, so there's a bit of confusion in the literature in terms of, so a top jet is a top jet where the light curve, you see it when the jet is top. But here we start with a top jet, but the jet loses its topness because all this side, the structured jet, or we call cocoon, people have used different terms, that's acquired during the interaction. So yes, you start with something that's 16. One could put a structure on there, but then it doesn't, I mean, you're just adding an extra degree of freedom. But basically, you're basically at the very moment, so this is a structured jet, otherwise you wouldn't see those light curves, you will see a very sharp decline. So they're structured, but they start as a top, because it starts as a little thing, a little energy injection, you know, which is constant, but then it becomes a fully structured jet at the time that we see the light curve.
I understand that, but my question was different.
Okay, so
I mean, that was not, so the light curve where they were fitting the data, I think were done with a uniform jet. And I was asking whether you have computed the light curve, I mean, as a function of the remnant, like a hyperneutron star or stable neutron star, or with your beta modeling.
So, okay, so for, you mean this last one? Yeah. So, okay, so the first one was done with, an analytical fit, right? With an analytical fit to the remnant, right, and not the top jet. It was an analytical fit to the remnant structure, which was not a top hat for the jet. Was the ejecta in which it was propagating was an analytical fit to data. So that was for the first one. For the second one, we're doing, for now that we have this better modeling, we're actually revisiting GW and see whether we can constrain further from the, so it's, yeah, so we're doing it as a part of a follow-up indeed. Yes?
Could you say a few words about how the jet forms?
Yeah, right. So that's a tricky, it's still the sticky point. So I have to go many slides back. So it was mentioned early on. So so it's the way we still don't know how to quite form jets. So this is the relevant slide on the topic. So the idea of a jet, if appears, right? So what we best believe is that there have been actually two, let me just go one step backward. So there have been two main ways that have been discussed to form jets. So one is neutrino annihilation. So that's been one proposal. And the other has been mediated by magnetic fields. Now, neutrinos seem not to have enough energy, so they're no longer considered as much, whereas magnetic fields are considered the main one. Now, the thing is, like, in order to have a jet, you need to be able to generate some funnel type of jet via magnetic field. So that's where the simulations are starting to, they're starting to look into. So we're not quite there to say, okay, we really have a jet. What we have as right now is some evidence that magnetic fields after a merger tend to rearrange itself in a configuration which is conducive to producing a jet. So this was the 2011 paper, and this is from more recent one, which we did with it's the same code, the GRMHD, whiskey MHD. So we show the same thing. We study more cases. Other groups, Ruiz et al. Also have done others. So we all find the same things. But yeah, I wouldn't call this jet yet. So it's one of the biggest problems. It's not only just here. It's AGN, so basically on all scales. How to drive jet is a general big unsolved problem in astrophysics. But now this area, this research is basically quite driving it because of the relevance. So there's been an outburst of research because, yeah, motivated by these observations. And I saw another hand.
Tom, one of the plots that you showed when talking about your own simulations was a plot of the, I think it was the delay time between the gravitational waves and the gamma rays as a function of viewing angle.
Right.
And generally that was smoothly evolving, but there are specific viewing angles where there were jumps.
Yeah. So so I didn't go too much into the So there's a lot of so the way they're calculated. Let me go actually there. Right. So the way this is calculated is basically is the region in which the photons sorry is the region in which it becomes often thin. So which varies with gamma. Now the other, so the parts, first of all, the parts below a certain angle, they becomes less reliable because it's the part where the jets start interacting with a lot of the side stuff. So there's a lot of fluffy. So it becomes, it becomes fluctuating, but because it's actually, so the time delay is a gamma square factor in the denominator, as you know, and the outer becomes no longer a uniform function gamma, the jet, because it's interacting with all this side, and it's a sort of turbulent. So that's basically, these gaps are more reflecting like encounters with different material that it's more or less fast, makes it more or less fast, different angles.
Thank you.
Last two questions. Okay, so Sultan.
I just wonder if the VLBI superluminal jet doesn't give you the same inclination. Or is it,
Right, I don't remember what but all the inclination have been actually, Will and Katerina will probably know. The different measurements have all given around like 20, 30, has been like sort of.
I think if you say 20 to 30, that probably encompasses everything.
Everything, right,
I don't specifically know what the VLBI jet inclination is.
What is that, right, okay.
are they comparable accuracy, or is one much better than the other?
The gravitational wave inclination measurement's pretty bad.
No, I mean the VLBI or these.
The LBI, I don't remember the VLBI, what they say there on the
VLBI is
English.
about 20 degrees uncertainty.
Okay, right, so,
that's
yeah.
So I was intrigued by you saying that the magnetic fields arrange themselves without worrying about the starting position. So if you have your two neutron star dipoles and they are oriented like this versus like this.
Right, so we haven't studied fully the entire, so in this paper, the one that I showed, so we studied a few cases. It is possible that there may be situations where, I mean, actually one thing I should say, well, I don't know, we don't go back and forth, I can just say.
In the AGN case, it seems to be sensitive to what the orientation of the fields are coming in.
So it is possible, but one thing also to keep in mind there, that a lot of the, so the magnetic field grows a lot as a result. So you're basically converting orbital energy. Somewhat goes into the magnetic energy. So there's a lot of winding up that happens,
Same
and that.
Same in accretion.
Right, same in accretion disk. So, but I say there is a certain preferential direction there, independent of where the orbital direction. So that I think it also depends on how much of the energy from the original magnetic field versus how much of the energy from the the wind up due to the orbital motion goes into. But yeah, it is. I mean, this is something exploration that obviously needs to be done. So we started with just inclinations, but they were not like hugely different. Also because neutron stars, which I mean, especially the ones that in field binaries that say they would tend to be not to to more to be inclined like same spins being more. Aligned with one another. But yeah, definitely the situation can change. And already among the cases that we studied, we found in some cases that the growth was stronger, there was a more clear poloidal structure than others. So already some differences in there. I mean, obviously at this point, there's no way we can compare anything with data. But in the future, looking forward, when we have more data, then ideally one can go to the second order where you say, okay, if you measure spins or from gravitational waves, then how that correlates with the type of electromagnetic signature that we see. So that would be quite a bit of learning in years to come when we have all data from both parts. So yeah, and then that will motivate also more simulations. Yeah. this exploration.
Okay, let's thank Rosalba again.